Even if they're not zero here. So it's better to these nodes, and specifically also make everybody who is here for Friday afternoon talk. That's not that. Now, the topic is not that close to the topic of the conference, and this is a talk mostly in differential geometry. But there will be some relation with this, and a little sideways into generalized geometry, which I hope I'll touch upon. This is a problem that started long ago, and the meaning here of isotropic killing fields, of course, means a vector field, killing vector field, a vector field which is generated by one parameter group of isometers. Well, these are basically the infinitesimal isometers in a sense. And isotropic means killing vector field of non-zero, which in particular means that the metric behind all of the talk is not a positive definite right. So it's not Riemannian, it's something which used to be called pseudo-Riemannian, sometimes sub-Riemannian or sub-Riemannian for motions. And because it's a little bit on the side from something like geometry, I'll start with some linear algebra for first-year students. A little bit. Now, suppose we start with vector space, dimension 4, which is oriented. And we take a scalar product of indefinite signature, which is actually split. We call this split-siganture sometimes. I mean, this is the kind of split the algebras clip on for the algebras and so on. And the group of connectors preserving the isometries which preserve the orientation, this sign is not even connected, unlike SO4. So there is a specific called the connected component that is presentation. And then for this connected component, we have something reasonably similar to the composition of SO4. This is like the only non-simple special orthogonal group in the sequence starting from SO2. Special killing. And non-simple means up to double coupled, we call it. And in this case, these are the corresponding dual real reduced to SO2. Now, once one starts with a product acting from a vector space, then from a presentation theory, it's known, a very basic one, that the space actually is not like fundamental representation, but finds a product of two. And this, in this particular case, so this particular case looked at the algebra, and the two factors in the tensor product are actually two-dimensional, real vector space, and because SL2 is the corresponding structure group, the corresponding form, the corresponding structures in these spaces are just two symplectic volume forms, symplectic forms which eventually represent volume. In particular, once one gets this representation, it's, well, we can call this spinor representation, comes from spinor language anyways. The corresponding scalar product is given by these two symplectic forms, so they are basics of it. And in these terms, of course, we always get like orthonormal bases, meaning length plus minus one vectors and mutually orthogonal. But for a space of this type, to signature, for this construction, one gets a little bit different basis, which is still kind of important. This technology knows that there are constant physics and some papers which are related to integrable systems of these structures appear there. And if one takes this basis, the reason I'm putting that like in a square is that one can observe standard related structures out of that relatively simple. In particular, if you take any two isotropic vectors, sometimes I'll call them null. This is the physics again. And mutually orthogonal, then they span this kind of maximal isotropic subspace because 2 dimensions is maximal isotropic. And they are either of this type or of this type in terms of that representation which we have in TensorFlow. Well, formally here it means that we need to fix one of the vectors, and then the representation actually comes out of using appropriate schemas. And this is analog of the fact that, well, if you take the so-called spinor line, it determines maximal isotropic. In the positive definite case, the spinors are complex. Here, I think they're real vector spaces. And in the complex, in the positive definite case, the projected lines of this local spinors, in the linear case, in the linear algebra terms, corresponds actually to maximal isotropic complex subspace in the complexification, which is the same as complex structure. And this is where the basic twistor construction comes from Penrose. Now, in this case, however, we can consider that if we have 2 such vectors, and existing such vectors in the manifold, usually this is what most of the local papers are about, what happens if you have isotropic vectors or vector fields. Actually, one can define, and once you have the 2 vectors, there exists unique complex structure with this property, and moreover, unique, sometimes it's called quaternions structure, called the square plus identity. On one and negative on the other. So this complex structure coming back means that we have the standard graph from here to here. And if we take, let's say, complex structure which sends this vector, it's uniquely extended down. It doesn't depend on the choices we do. Actually.
So just to talk it
yeah.
down, because generally when you have signature, you have this code, right? So when you are pushing this product, then you are kind of this. How does this behave? Because the matrix seems to be product.
No. Basically, you still want, because here, of course, if you want to go back to the spinors, you again represent the vectors as matrices. But nevertheless, the matrices are vector space. And you can talk about what is a complex structure of a vector space. This is something to square some endomorphism in this terms. Okay. And the point is, usually, if you have positive signature, the natural structure which comes is attached to a definite product, positive definite scalar product. It's not just one complex structure, it's like a whole sphere of complex structures, same orientation, compatible with the metric, which gives this para-hypercomplex structure complex or similar and twistor spaces. Now, for indefinite, the corresponding analog is not a sphere of complex structures, which are like a unit. It's actually a complex structure, and this, which is like a product structure. But the idea is they still unlike a unit. And the product, one takes the square, is still a product structure. Yes, they unlike a unit.
So this is the analog of hyperkeller for.
Yes, this is analog of hyperkeller. And again, here, the basic idea is you can determine one out of the first row, And then you can determine the product structure by sending like the first row to the second. So the complex structure makes pretty much sense the column to the column, the product row to the row. So what the result is, well, if like the quaternions are the algebra corresponding to these strange complex structures, the imaginary quaternions, here the corresponding structure, which is again associative algebra, are the so-called split quaternions. I would say that this again, as associative algebra because we get products, is the same as the standard algebra of two-way matrices GL2R. But the reason we choose that representation in this algebra is precisely the existence of that strange structures here on the top. And for them, again, if we use this presentation and again use what is conjugated in the same way, and the algebra here leads to pretty much the same idea. This is precisely, we close it, what will happen for the result of the game. Plus, again, one has that, and that, again, well, crucial differences. In this case, you have divisors of 0, unlike the quaternions, so this is not like invertible operation. But there is one more thing here, if I go, that this identity is pretty much the same for quaternions and split quaternions, leads to something different. Now, if you have a quaternion which is purely imaginary, the result here is that with difference. And if you want to have complex structure, if you take imaginary quaternion and its square, suppose that 2 and p are equal, its square is actually plus or minus depending on the sign. In particular, if we take this kind of compatible complex structure, compatible means isometries, and depending on formally the corresponding scalar product, have this kind of strange observation that we have two complex structures on an oriented plot space, compatible with the mean conformal class. Conformal class, of course, this means commutative class, but the commutative is vector linear algebra. If you told me we have this kind of identity with that, this is kind of for the cubic algebra on top. If the norm of P is 1, then this negative 1 means the two will have scalar product with vectors of length 1. Of course, scalar product is less than 1. Or
this can be quadratic form, right? The analogous form.
Yeah. In a sense. But the idea is we want to parameterize complex structures and kind of identify which are compatible with positive and negative or indefinite structures. And complex structures compatible with the positive definite metric and orientation. It's actually for a two-sphere because these are pluses, A is 0, and then the sum of the squares equal to 1 identifies all kind of parameters, all complex structures compatible with the plot space and orientation in the metric. Now, and this is what is behind this perspective. Now, if one has the same identity with this, and we put some additional that once you take the corresponding commutator, which is sometimes commutator, if you take the commutator, in this case the commutator is kind of proportional to negative identity with positive number. Here, commutator is proportional with this identity, with this inequality is proportional to positive identity. So the square, I mean, not the competitor itself, the square of the competitor is positive identity. And this means that you can find levels, actually, because of that structures, they are two-dimensional. And we additionally want to be orientable, meaning one needs to choose orientation to get the uniqueness of the conformal class. This is similar to that choice of volume function versus factors. I mean, they are not unique in order to determine the corresponding problem. Now, this is in a sense why I'm mentioning this particular property is that these two, actually this one identity, leads to that notion of bihermitian structures which comes out of generalized scale. Now, based on that nice split quaternions, one can define just in the case of hyperkeller and actually hypercomplex for 12-dimensional manifold, a triple of endomorphisms with this property, and in case of hypercomplex, we need integrability. Here, the integrability is the same. I mean, there is this tensor condition, but what it hides is that the corresponding eigenbundles, complex height of real, are involutive. They are closed under the standard bracket. Now, in particular, want to use this as a bihermitian. I want to use strict word. And this could be positive, definite, or indefinite if we have complex structure with this property. And this means this norm is not one at any point. Otherwise, what happens if this is one? If this is one, what happens is that actually the two structures coincide with up to sign. I mean, it could be plus or minus. And the idea is we don't want them to be equal. So pretty much this corresponds to the fact that we have two complex structures which are not equal at any point on the space. And this is something one can say bihermitian, sometimes pseudo bihermitian. Yes.
The point that some description to the even dimensional. Okay, multiple by 4.
No. Yes. So the whole point is once we go to this triple of structures, the requirement of the dimension to be divisible by 4 is not necessary. No. That's the very first immediate difference between indefinite and indefinite chain. Actually, this type of structures, because it's down with delta R, this type of structures easily exist on two-dimensional space. And one of the maybe the simplest possible results for the representations is that the GL2R is associative function. Every finite-dimensional representation is actually a direction of the basic representation, GL2R in R2. So in particular, yes, one can start with any dimension. But if we ask, I mean, if this is constant, we get this actual, if we start with complex structures, where complex means integrable almost complex here, because they are random morphisms. And if we start with constant, not P, this is lambda. P was from the previous slide. So if lambda here is constant, then one gets this hypercomplex or para-hypercomplex family. And the point is, when we ask also for existence of metric, it's not that much. Even in dimension 4, this low by 4. Before I go further, just since this is generalized geometry conference, which I don't know how many general geometry talks I missed a lot, so I don't know. Maybe, comment, but the bihermitian structure basically is related to something called general scalar. And the general scalar is related here in the following sense. I mean, we can start with these endomorphisms that sometimes called generalized tangent, tangent plus cotangent, which have a square negative identities, have some kind of current integrability, and some compatibility with pairing, because this space has natural pair, which is exactly split-siganture. Now, if we have commuting structures like this, we call them generalized scalar if the restriction of that pairing, which is canonically given, onto, let's say, one of eigenspaces, the product. The product has square plus one, so it's plus or minus eigenspace. So let's say the plus eigenspaces. When one takes the product restricted on it, it's positive definite. And that's what general scalar is as a definition from each and both theory. Now, if you ask only for non-degenerate, non-positive definite, what one gets as a result will be, well, let's say, general pseudo-scalar, which means a complex with metric which is indefinite. Still complex association. Now, well, at some point we were looking at what happens in dimension 4, which is the dimension where general scalar actually has natural representation, for by definition, it's almost different, only very little difference. But in this case, the possible generalized, the possible metrics also for indefinite, which are compatible, which have compatible complex structures, necessarily have either positive definite signature for 0 or split signature to 2. Because the other signatures 1, 3, and 3, 1 cannot have compatible complex structures. And vector of length 1 should have image under the complex structure, again, vector of length 1. And same for each. That's how split signature actually is appropriate for compatibility of complex structure. Okay? And that's how we get it. So the previous definition for bihermitian is one of the consequences of that generalized pseudo-scalar result. That generalized pseudo-scalar structure will define bihermitian or pseudo-bihermitian, but there is also differential condition. And the differential condition in both cases actually is because it's pretty much local result. Most local results transfer from positive to indefinite signatures. It actually has to work with one structure, which immediately restricts if we want to look at complex surfaces, homomorphic Poisson structure simply needs homomorphic section of I think anti-canonical. And then one gets immediately the restriction of what surfaces you can get. Poisson structures are described before. Now, because I promised differential geometry here, the differential geometry goes a little further down along. Again, this is local result. If we have kind of complex structure, triple or almost complex structures, then one has unique connection which observes them and doesn't have problem. This is a little bit unlock of discriminating geometry fundamental theorem that we get unique connection without problem results. Now, for many structures, plus structures in different type of methods, for many structures, one gets either resistance or non-uniqueness and non-resistance. And to get both resistance and uniqueness like this is a pretty special. Of this type is a pretty special problem. Doesn't take a lot. So in this case, actually it does. And this leads to this property of once you have a metric and the structure, or even all the structures, you still have this kind of various complex structures or product structures, and this type of thing will give me a dimensional distribution, which actually correspond to precisely maximality problems. And you can describe maximality problems in this way. Now, if we have already, I'm talking about the indefinite case now. Now, if we have a metric for which these are skew symmetric, this is called para-hyperhermitian or neutral hyperhermitian. Well, usually at this point, for people who pay attention, I kind of apologize because this terminology of para is a little bit strange. It came first time for, I think, like Lieberman in the 50s when she called para-complex structure, this type of product structures for which the trace is zero, the positive and negative. I don't know those are people in dimension. There are things like this, although, well, the para is appropriate to go with not just hypercomplex. So para-Keller, para-hyperkeller, and so on. When you see this non-para notation, this is what we go. And well, this also gives kind of a nice opportunity, some point for people to look at complex structures. There are para-complex cycling. And there are things like normal complex structures. So I guess this terminology will lead to excellent paper with title paranormal structures. So we go to this para-hypercomplex still of paranormal structures here. And these are the corresponding problems because they are symmetry. But if you want that, you immediately see that this S is not an advantage. In order for this one to be skew, S is actually sort of anti-isometric. So G of S x y is actually negative, so same as P. But if these are the two are all forms, the basic observation is that this form coming out of S and P again is of type 2 for the complex structure. In particular, if you go over manifold and assume that structures, what we get is non-vanishing to 0 form. And non-vanishing to 0 form, I'm talking about 4 dimensions. Here is for 4 dimensions. Here, and it's actually 4, so that n is 1. And existence of the form, of course, is logical restriction. We talk about complex space. Here, it doesn't mean trivial canonical normal observation %. Because there are many non-trivial restrictions where the logically trivial canonical bundle is not homologically trivial. If you go outside the trivial world, this happens a lot. The basic example is like cosines.
But just because now I realized that I'm missing something because of course everything is very local, but then the kind of integrability of your Nyaya house tensor, you are indeed with a Nathan O'Neill condition like
yeah, this is probably this is local because it's point by expansion. But if you want this global everywhere, then yes, there will go.
yeah. But the indefiniteness of the metric doesn't matter.
No. Again, you don't need to have a metric at all in this case.
Okay, so
actually, in many cases, you don't. And the first observation I mentioned here is this basic example, right? If you have structures there which are compatible with the metric in distance, they have symmetric forms and so on, you do have dimension divisible by 4. But this is not enough for existence. It's not like hypercomplex where you can find hyperhermitian metrics. Because you cannot do this strictly simple linear algebra which symmetrizes, you may end up with the generator 0. You symmetrize indefinite things. And in fact, in version 4, this is relatively Well, not involved, and a little more careful look at linear algebra tells you this fact that, in fact, that condition for existence of volume function, particular two-dimensional subspaces, is important because this means that particular two-dimensional subspaces are necessary oriented. And one can get by elliptic surface or this type of S minus in all of them. I mean, this is by, of course, this portion of tolerated. This is non-carrier. They admit para-hypercomplex. You can find them, but they do not admit such method. However, a good point you mentioned, Paul, in fact, is if you start with compact, space para-compact hypercomplex, then up to a double cover, you know that the space will be. So just like the double cover by elliptic, and then double cover of this particular S minus again S minus, but it already means this type of thing. And there are some strange parameters there instead of making one plus of it. Now, the other is, as I mentioned, what is a twistor space. Now, in this space for the para-hypercomplex, the twistor space is basically this direct product space, a real space. And B here, which is determined by that, is actually, if you remember, this is like two sheets of paper, which, if one takes again similar to the stereographic projection, these are two copies of the disk. This is identified easily with the disk. And then the disk approach is C, has complex structure, and then again, one has this special topological type of complex structure of this type, where if you have a point P on N and triple ABC in V with this property, then we can form this as a complex structure, the point P, and then we have the standard form, which is like it's the topological definition. In particular, in this case, just as in the positive case, the projection of this space on D is homomorphic. The projection on N is not. Also, the structure varies. It's not like vibration on N, it's on D. Okay. Now, when we started, actually, I started with this the relation between filling fields and complex spectrum. So, in this particular case, in the indefinite method, the distance of filling fields is true, which span some null space related to the complex spectrum. So, this linear algebra, the question: what happens if one needs this integrability? And the first observation that we had on the row is if you have parallel and orthogonal vectors, which are isotropic of null, again linearly independent, because you may have easily parallel, orthogonal, and linearly independent. This is indefinite C. You have your own level. Then one can say that this as a metric is pseudo-carrier, then the Ricci flat is a property of the metric similar to the Ricci flat in the standard positive case. And when this is compact, actually restrict this space to these two options only. And the reason for that is, well, para-hypercomplex, I guess you can guess this paranormal structure, which these two forms are called para-hypercomplex. Actually, the study of this type of range structures with quaternions related is started with a paper by Ignacio teaching about para-hypercomplex, and of course he didn't use para-hypercomplex. The standard notation also is hypersymplectic, although hypersymplectic is used for other things too. And hypersymplectic is because the three forms are symplectic. three symplectic forms and some special properties. I'll mention at the end where the structures appear and which experiments. Now, this is if one starts with parallel vectors. Now, what happens if we relax a little bit in the requirement? Now, if you have any vector, you don't expect any special properties of that structure, its own non-integrability. But the one observation we have, which is based on that, is first, if one starts with one killing vector field, which is killing is again, it's a local, like in infinitesimal isometry, no means isotropic. And these are called two-dimensional, which is maximal, no distribution intensity. This is local result, non-globality. Then this distribution is actually integral for inverted. And then what we kind of observed a bit later is what happens if you get two, and if one has two, not one, vector fields which span this type of grid, of course locally you can find, but it's not necessarily killing. Locally, just no vector fields you can do, but the idea is to be killing. Here is killing. I mean, if one is conformably killing, then this is happening. If both are killing, then this the distribution is parallel, but not the field itself. And the question is, this is commuting. And the result is basically what, took a long time to observe that, even by next dimensions, is if we start with this linear independent orthogonal killing, then this is necessarily a whole para-hypercomplex structure, which is also para-hyperhermitian. Now, when the vector fields can help are parallel, they commute, but if we ask only for commuting, this is what happens. It's kind of, and this is again pretty different from the post-detector, because the existence of two independent killing fields that they cannot be known do not lead to integrability of specific structure. One can define one's complex structure, because one needs, of course, equal nodes, but still existence of orthogonal equal nodes vector fields leads to almost complex structure, not integral. Here, but property being as properties.
So you mentioned that there is no integrability in a sense.
In a sense, the integrability comes after you assume that vector fields are killing. This is specific type of vector field. If you don't assume killing vector fields, then killing is again differential condition. Then you get the integrability. That's the name of the word. Okay. Now, basically, in method 4, one can get positive or negative property with this, which I already mentioned. The first is something it's in out. So the second is what is the description in terms of structures which come out only of differential forms on a space. And basically, this strange para structure, hypercondition structure, comes out of, again, three forms with, well, this is with negative. Here you get positive, you get what is para-complex, what is hypercomplex, hyperhermitian. And in case of coordinations, somehow the integrability leads to the fact that you have this kind of differential system. This is for 1, 2, and 3. So these are three differential equations for the two forms. And because the forms are non-degenerate, then such one form exists, but they are usually different for the different forms. the idea is three forms to be the same is equivalent to this integrability of the same. So just the first existence of two forms of this property algebraically leads to just almost para-hypercomplex spectrum, non-integrability, and the differential condition. And then again, the para-hypercomplex is this differential form. Now, one can, because if you remember, these two again define a 204 is important. Then what one has is one can determine if one fixes the complex picture once for the complex, then it's integrable and part of para-hyperhermitian if we have this type of two form, this property and this property, someone for. Now, this again, the previous lemma leads to the fact that this form here, in this form, if theta is 0, which is equivalent to para-hypercomplex, means we have closed the 0 form. And this already leads to this para-hypercomplex. And then, well, this is one of the, forget this block here. One of the observations which was done before, that if one gets compacted this type of para-hypercomplex, then the result is here complex torus for a primary diagram. The reason, well, if you have compact complex surface with trivial canonical contour, homomorphic trivial directions, then you have these two examples, and homomorphics entirely trivial, like bilateral surfaces, they don't have trivial. Numerically trivial, square is trivial, in the K3. And the only question, so in this proposition, of course, you get minimum surface, you not have board, you not have exceptional proposition. And so the reason this is called proposition is that one has to somehow cancel the K3 surface classification. And the reason why K3 surface is discovered goes is reasonably deep from the actual geometry point, otherwise no. And the reason is that the K3 surface, the K3 surfaces do not admit symplectic forms of orientation. The first proof of this actually uses the very initial Zeiger-Fulton invariant in manifold. And then, well, one can do it a little better. Faster, but yeah. Now, in a certain way, one can describe these surfaces, what are the para-hypercomplex structures there. And this is the type when we talk about the factor. I guess I should have the definition. Yeah, maybe this is a slide I should show first. Also, Polar surface of prime. You don't need to know by how it is. So this is something which is again a factor of the whole plane, C2, but the group which acts freely and properly discontinuously is not a billion. So if you have a billion lattice, the result is complex tolerant. You have this strange group generated by this type of linear or affine functions under that and that restriction, the result is you have well-defined, really and properly discontinuous acting group with a compact portion, which is primary polar surface. The reason I'm using this description is because it gives nice global coordinates for representation. the global coordinates of C2. Otherwise, logically, I don't know who else mentioned, but this is like elliptic vibration over the tori, the complex tori, or elliptic curve, which is not necessarily trivial. It's not like the product of the elliptic curves. And this will be again. And elliptic vibration, I mean, without singular fibers, it's like principal colors. Without singular fibers, without multiple fibers, this is very good. Now, in these terms, one can get that statement, what exactly is the form of this omega 1 and omega 2 and omega 3. Again, this thing here should lead to homomorphic form. And there is one for some constant form. So the idea is once you have the homomorphic form omega 2 plus psi omega 3, which is here with Z1 minus Z2, when you count of that, is Z1 minus Z2 here with all this expression, actually is all the time. And the one thing which remains is for omega 1, and again for omega 1, the other conditions lead to that type. And that type of arbitrary function is a smooth function with some strange differential equation. Now, this differential equation actually is, because these are two forms, we have two forms, equal four form of four-dimensional space is actually one scalar equation for phi. And in nice interpretation, this would have been elliptic. In this case, equation like this is something which is called ultra-hyperbolic, like the wave equation where the canonical unionization has one plus and two minuses of phi rest. Here we have two pluses, two minuses. And as you know, when it comes to indefinite signature, the topology is not related to that. And the main trouble is precisely that all of the theories starting from the linear classical Koch theory, representing cosmology classes in terms of harmonic form and so on, fails quickly in indefinite signature. Maybe I should say here there's a basic example is if you look at two-dimensional tori and assume that you have metric signature 1, 1. It's indefinite. Then the set of, let's say, harmonic functions, where the class is coming with the metric sign, the set of harmonic functions is infinite dimensional vector space, or just zero or constant. It's infinite dimensional. So in this sense, any attempt to relate topology with equations of this type is out. Question. Now here there are a few remarks quick, because I'm talking about parallel vector fields, because this was quite clear. And this appeared as one of the cases for that result if you get two parallel fields in general. That first we have flat metric, but we have non-flat metrics, which is still falsifies any function with this type of condition. And actually, it's very easy to see that function which depends only on one of the variables, Z1 and Z1 bar, not on Z2, satisfies that. So it's again in dimensional set of solutions. And then in these terms, this vector, whatever we choose by constant or function of this type on the curve when we represent the United surfaces of vibration, this case both lead to null vector fields, and we have parallel vector fields, so that we have like infinite dimensional families of metrics which have fixed null parallel vector fields or null parallel vector fields. Even in the compact case, the set of solutions will be large for this type. And well, one can say a little more what happens. Next is if we drop the requirement for closures for para-hyperhermitian and see only integrability part without actually closed forms requiring the forms to be closed, then we don't have trivial canonical quantum, we don't have trivialization. But we get like smooth trivialization in the topology, you know, and then one gets that first one class manifold. Again, the different effects don't have anything but one take component perfectly fine in first class. And it's reasonably straightforward, that explained here, how to get the list of all possible. Again, one gets that, the result eventually looks like this. Now, if one gets this type of neutral, meaning split-siganture for manifold, and just conformal Killing vector fields, which are independent, and this is already a big assumption. Then the result is that M is slightly homomorphic. Underlying smooth manifold is diffeomorphic to one of them. It's here. Here we don't even need much of this carbon free surface because we don't have global vector fields, which is not much. And these are pretty much the list of possible complex surfaces with vanishing function class minus the K. And as you see, only the complex topology here actually is a Kelvin surface. And I mentioned the primary. So properly elliptic, the terminology, this is the nuance from the like it's before. Properly elliptic here again means elliptic vibration over a curve of possibly higher genus. Those if the curve is 0 or 1, we usually get something around the layer surface or it's called top surface. But if you have curve of genus R1, possibly with some singularities, then elliptic vibration means elliptic vibration without singular fibers and isolated multiple lines. It corresponds to singular points in both places. These inner surfaces, well, to describe them one, again, this is very easy. To use a universal curve, that portions of C, the line, complex line, times the unit disk and the action of the group, which is a solid group, which there. One gets that. These are these surfaces of type 70, and they're the only ones who are vanishing second Betti number. I mean, the 70 complex surfaces classification is capable of question for a long time, yes. And there are some advances, recent mostly by Andrew Telekom, but still, as far as I know, it's also a question. And the interesting point, the difference from positive case is the converse. If we take the list here, we see that O in this list 1 to 3, including some of these types and some of the Hopf surfaces, do a good matrix and this type of vector. It's kind of the existence and we describe because if you want to ask for, let's say, complex surfaces, it is something which is known since late 80s, and if you need positive definite metric then the result is this complex topology, this hot surface, and the KP. And the only one. But here we have many, and actually we have many. So I don't know, let me see how much more I can. We have to go. Maybe I'll skip. There are examples. Like what happens if you want to surface, how exactly one constructs. Now I will not give the details, I'll just explain that for primary top surface, actually this is like a really group here. Actually, two times as one. We have global non-dimensional vector fields, and you can find pretty much homogeneous methods here relatively fast. Same is for direct surface, where you can find nice global vector fields, and the result is there. Now, the last couple of minutes, I want to say a few words about the possible motivations about this result, about this topic in general to be considered, and this comes out of that so-called self-duality. So what is a self-duality? In general, you can have a four-dimensional space and a metric, regardless of the signature, but we want for 0 or 2, any of the two. Then the hot star defines involution, and in fact the curvature of the separator is like in matrix formulation. What's good of matrix representation of the curvature is that this component here corresponds to the so-called places we reach in if D is 0, the matrix is Einstein, if and only if. This little tau here is like the corresponding trace of the matrix, and this corresponds to scalar curvature. These two parts, W plus and W minus, the sum of them corresponds to something which is called conformal value tensor. Conformal value tensor meaning the vanishing of this is equivalent to conformal flat. So it takes conformal flatness. And of course, vanishing of each separator is like half conformal flat. And instead of half conformal flat, one uses self-rule or anti-self-rule for these two. And these are the corresponding endomorphisms of number plus or number minus. And on this, for example, space regardless of the signature again, if one has Hermitian surface and one complete vector field, which is null, if this vector field is homomorphic, meaning resulting in the complex structure, then the homomorphic vector field, then in Keller case, basically every field is homomorphic. It's not Keller, you can assume that it's not homomorphic, maybe necessary, actually, what I said.
That's
similar. Yeah,
sorry. That matrix was the matrix of the whole operator.
Yeah.
Operator.
That's a Keller space. This one. This is I think Zinger top type of like the Zinger and top use that to go this kind of expressions of the basic characteristic and signature of top manifold in terms of norms of that parts of the curvature.
And just to be sure that the primary result, the one with the possibilities, the result can be theoretical properties of this matrix.
No, the other way around. The previous results lead to the fact that this thing here is necessarily yes. And the last moment is actually one can use this reduction process for hypercharacter or Keller to construct using moment maps level sets with some additional dependency to construct quotients similar to symplectic quotient with equivalent to GID quotients standard terminology. And the reason to look at that is this kind of, well, this is, I should say, pseudo-corollary or para-corollary, depends. So it's better that if one wants to consider the so-called instant bones, but the instant bone in this case means that I mean, this consequence here. But the idea is again that the cells blow apart of the curvature vanish. And this type of instant noise for positive definite cases is exactly what the instant on model spaces depending on it is. Here, one can use that construction to show that if one starts with four manifolds with para-hypercomplex or para-hyperhermitian, which are actually in the forms, then the corresponding moduli, the smooth part, and this is specifically tricky because the smooth part might be very small. I actually cannot say what the smooth part is again para-hypercomplex. The same thing works, and basically one of the main points in that paper by teaching of self-valid equations of curves is the existence of the hypercharacter structure there. The existence actually follows precisely this type of process of relation. One can go further to say that the instant on-moduli spaces in complex surfaces with fixed metric somehow inherit the form, the properties of the metric. Meaning if you have hypercomplex structure, the moduli space will have hypercomplex and so on. Here it's in a similar way. And the last to notice is that these instant tones, of course, they're related to self-duality. And self-duality, especially in split-siganture, was considered first as generalization of many of the so-called integrable systems, called the vector trees, canonical, the shear,